Okay, we're picking up where we left off in the Taylor and Maclaurin series section of the calculus textbook. In this video, we're going to talk about the binomial series. Okay, so what we want to do is we want to find the Maclaurin series for this function here. This is f of x is equal to 1 plus x to the k power, where k is any real number. So k is any real number, meaning it could be a positive or negative integer. It could be pi or negative pi, anything. Okay, and so what you can think about is if we can find a power series representation for this in general with just like a general k, then this is going to open the door for finding a wider array of different power series representations of functions from the standpoint when you consider that we can, so as we talked about in the previous video, we had that list of Maclaurin series. Well, you can use those as like base series, and then you could differentiate or integrate or pattern match to find more power series representations. And so you can think about, this opens the door for radicals, for example, rational functions, radicals in the denominator of a function, things like that. Now, you might say to yourself, well, yeah, this is kind of restricted though. It's not that restricted, but we can only do so much with this. And that is true to an extent, but just to point this out, remember, x can be, you can replace x with like anything. Okay, so what if we just had the square root of x? We wanted to find the power series representation for the square root of x, and we had the binomial, we have this formula for the binomial series. Well, okay, we do this. 1 plus x minus 1 to the, I'm just going to put k, but in this case, k would be 1/2 because it's the square root. But just think about this in general though. So look at this. This is, if you simplify, you get, it's just x, right? So x to the 1/2 of the square root of x. But we could plug x minus 1 into the binomial series formula. You see, so you can eliminate that 1 if you need to. Or, I mean, it could be anything. Like we've seen examples if you had, if there's a 2 out front, 2 plus whatever, x over 2, I don't know, to the k, you just factor out a 2, and then you take out the 2 to the k. K is just a number, and that just ends up being a constant, and you put it into a form where you can do the pattern matching. So the point is that list of Maclaurin series is a lot more powerful than you might initially think. There's a lot more offshoots that you can create from that than you might initially think, strictly just from pattern matching. But if you also add the potential for integrating or differentiating both sides, or like multiplying, we could do x times 1 plus x to the k, right? We could just bring x inside the power series. When you bring all those different strategies together, you have a lot more versatility than you think from just that small list of Maclaurin series. Okay. So, all right, let's find the Maclaurin series for this. So when you're developing a Maclaurin or Taylor series from scratch, remember you have 2 columns. On the left side is the derivatives of the f of the function. It doesn't matter where the center point is. The center point has nothing to do with this, with what you're doing on the left side here. No matter what the center point is, you're doing f of x, f prime, f double prime, f triple prime, until you can see a pattern. Okay. So if we so here's the function, 1 plus x to the k. F prime of x, you bring down k, it's 1 plus x to the k minus 1. F double prime of x, you bring down the k minus 1. So it's k times k minus 1 times 1 plus x to the k minus 2. F triple prime, you bring down the k minus 2. 1 plus x to the k minus 3. And so now we can see a pattern here, and we could say what the nth derivative is. And what you get is, so it's like k minus 1. And again, this is what you would do for any real number. K doesn't have to be an integer, any real number. K minus 1, and then k minus 2, and then they put dot, 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 and it says k minus n plus 1. What that is what's this last factor going to be? Well, we can see it's always going to be k minus 1 less than what the power on the 1 plus x term is. So like the last factor here is k minus 1, this is k minus 2. The last factor here is k minus 2, this is k minus 3. So it's k minus, okay, now, but what is, so we're doing, this is the first, this is the 0th derivative, the function, then the first derivative, the second derivative, third derivative. So k minus 1, that corresponds to the n, k minus n, k minus n, k minus n. It's the n, whatever derivative you're on, this is the 0th derivative. That's what the power on the x, the 1 plus x term is. So this is going to be, though, but for the coefficient, it's going to be k minus, and not n, but n minus 1. And then you'll have 1 plus x to the k minus n. So this k minus n minus 1 is k minus n plus 1. See? All right, so that's the nth derivative. Here's the formula. Now, on the right side, you plug in the center point into each of these. So f of the center point is 0, so f of 0 is 1. Here, f of 0 is k, f of 0 here, so you just, x is 0. So it's just what you end up getting is 1 plus 0 to some power, but 1 to any power is 1. So for when you're plugging in 0, it's just whatever the leading coefficients are in front of the 1 plus x term. So here it's 1, then k times k minus 1, k times k minus 2. So the f of the nth derivative at 0 is just this without the 1 plus x to the k minus n. Okay, now from here you go into the actual Taylor series formula. So remember, it's the sum from n is equal to, you could potentially adjust the starting point, but it's the nth derivative of x over n factorial x minus a to the n. So if you actually have a formula that you can just put for f of n of x, I'm sorry, that's not right. This is f of n of a. So the case might be where you actually have f of n of a as a formula, so you just go straight into the power series formula. That's what we're going to do here. But it might be the case that you don't have you couldn't come up with an exact formula like this, so you have to write out the first 3 or 4 terms and then come up with a formula from there. But they just put they just put this straight in here over n factorial, and x a is 0, so x to the n. Okay, and so that's the binomial series. This is the Maclaurin series of 1 plus x to the k power, where k is any real number. Okay, but this is a little different than what we've done before so far in this section, because now we've got this k in there. So we have to think about what happens with different values of k. So, but this is the binomial series. Now, it says if k is a non-negative integer, then what happens? What happens if k is a non-negative integer? Let's think about that. So you're starting with 1 plus x to the 30th, 1 plus x to the 100, 1 plus x to the 5th. What's going to happen? Well, you're going to, n goes to infinity, okay? But k can never be infinity. K is always going to be a number. So eventually n is an integer. N's going to get to the value of k. What happens then? When n equals k, what happens? So, okay, f of the kth derivative, you get, so, okay, let's see. f of k of x is, so k times k minus 1, and then you've got k minus k, that's 0, so this is just 1, and then you get 1 plus x to the 0, which is also just 1. So what's going to happen is you're going to go all the way to not k minus n minus 1. You're going to go all the way to the last number that's not 1 is going to be k minus n minus 2. So you're going to go to k minus n plus 2. So that's f of k of x. It's a constant. The kth derivative of x is a constant. Everything before that was had an x in it. Now you've got a constant. Okay, but n goes to infinity. So what happens after for the next derivative? Well, now it's a derivative of a constant. So that derivative is going to be 0, and every derivative after that is going to be 0. So wait, is the power series broken? You know, it's not. We're not. Is this not working all the way to infinity? Well, no. That's something to remember about these power series function representations, is that you can have a coefficient be 0 and then you can also take the derivative of 0 and get 0. So even though eventually f of the nth derivative is going to be 0, well, okay, but it's still valid, and every derivative after that is just 0 over and over and over again, all the way to infinity. And so what that means then, if you think about it, that means if k is a positive integer, then the series is finite. It's not an infinite series anymore. And this might be confusing to you. And what's happening is, this is what's happening. If you have 1 plus x to a positive integer, what is that? Think about what that is. 1 plus x to a positive integer power is a polynomial, just factored. But once you expand it out, it's a polynomial. Well, the power series representation of a polynomial, just because the polynomial has it, you might think a polynomial doesn't have an unlimited number of derivatives. Yeah, it does, because eventually you're just taking the derivative of 0 over and over and over again. So a polynomial has an unlimited number of derivatives. And so, but a power series, it's a polynomial though. A power series, that's what every power series is a polynomial. So the power series representation of a polynomial is just going to be the polynomial itself. We're going to do some example problems in upcoming videos. We're going to find the power series representation of a polynomial. It's going to end up being just the polynomial. And so if k is a positive integer, think about what the power series expansion of 1 plus x to the k is. It's just if it's the expansion of 1 plus x to the k. Like if you actually did the polynomial expansion, that's what it's going to be. And to illustrate that, it talks here, what we're going to see in a second, the coefficients of the binomial series are k choose n. So if you remember the binomial theorem, it's a theorem for expanding out a binomial like this. We learned this in algebra. It has this k choose n formula for the coefficients. Pretty interesting, right? Okay. Now for other values of k, so if k is not a positive integer or if it's a negative integer, any other values of k, then now think about what happens in that circumstance. None of the terms is 0. Because even if you had a positive number that, 150/37 or something, 1 plus x to some large positive number that wasn't an integer, well, it'll keep subtracting, and it'll eventually get to 0, but then it will come near 0, but then it won't equal 0. It'll just go negative and just keep going negative from there, all the way to negative infinity. So the terms for other values of k, the terms are never 0. So now if k is not a positive integer, then we have an infinite series. Okay, so what we want to do next, then let's use the ratio test to get the radius of convergence of this series. So absolute value of a sub n plus 1 over a sub n. They put here. So, okay, you've got n plus 1. So k minus n plus 1 plus 1. K minus n minus 1 plus 1. That's k minus n. So there's you go all the way to k minus n, and then x to the n plus 1 over n plus 1 factorial, and then n factorial, and then just, which you had, there's no n plus 1 here. And so you see all of this cancels. And the x to the n cancels, and so you end up with the absolute value of k minus n. You can't remove the absolute value here because k can be any number. You can remove it down here, and you can't remove it on the x. So they multiply the numerator and denominator by 1 over n, and you could bring it inside the absolute value because n is always positive. And then when you take this limit, this goes to 1, this goes to 1, as n goes to infinity. And so this goes to absolute value of x, which is, this limit of a sub n plus 1 over a sub n goes to the absolute value of x as n goes to infinity. So the ratio test is you pass it, and it's a convergent series when this limit is less than 1. So the radius of convergence is 1. Now, what about the interval of convergence? What about the endpoints? We'll talk about that in a second. But here's the coefficients of the binomial series is k choose n, and this comes from the binomial theorem. Really interesting. These are the binomial coefficients. Okay. The following theorem states that 1 plus x to the k is equal to the sum of its Maclaurin series. Yeah, so we found the Maclaurin series of 1 plus x to the k, but what about proving that 1 plus x to the k is equal to its Maclaurin series? It says it is possible to prove this, that it's equal to that they're equal by showing that the remainder approaches 0, but that turns out to be quite difficult. The proof outlined in exercise 85 is much easier. Okay, but it's that you can go ahead and they are equal. You can say that, so they never said it officially, but we wanted to say that this equals 1 plus x to the k. All we did was find the Maclaurin series of 1 plus x to the k, but they talk about that it has been proven. So here it is. Then they go ahead and set those equal here. There's the binomial series. Now, okay, so this k choose n, if you remember from statistics, k choose n is k factorial over k minus n factorial times n factorial. Okay, so but that doesn't look, these coefficients don't look like this formula, right? Well, okay, let's see. So when n is equal to 0, you've got k factorial, so that 0 factorial is 1, so k factorial over k factorial, x to the 0, so that there's 1. When n is equal to 1, you've got k factorial over k minus 1 factorial, and then n factorial is 1. But this is what? This is k times k minus 1 factorial over k minus 1 factorial. So you just have k, and then x to the first. Okay, when n is equal to 2, you've got x squared, then you've got k minus 2 factorial times 2 factorial, and then k factorial. And so the k factorial, you can write it as k times k minus 1 times k minus 2 factorial. So you're left with k times k minus 1 over 2 factorial. Okay, and so that's where these coefficients shown here are coming from. All right, although the binomial series always converges when the absolute value of x is less than 1, the question of whether or not it converges at the endpoints, so yeah, the ratio test doesn't tell us about the endpoints, so it depends on whether or not the binomial series converges at the endpoints depends on the value of k. Now again, they're not talking about if k is a positive integer. If k is a positive integer, then we're not even thinking about this with k as a positive integer. If k is a positive integer, then the series is finite. It converges for all real numbers. A polynomial has any input. So they're strictly talking about here, this absolute value of x is less than 1 is for any k that's not a positive integer. And whether or not it converges at the endpoint depends on the value of k. It turns out that the series converges at positive 1 if k is greater than -1 and less than or equal to 0, and at both endpoints if k is greater than or equal to 0. Notice that if k is a positive integer and n is greater than k, then the expression for k choose n contains a factor k minus k, so k choose n is equal to 0 for n is greater than k. This means that the series terminates and reduces to the ordinary binomial theorem when k is a positive integer. Yeah, exactly. So we talked about this. They're saying k is a positive integer, and then you just end up, it's still an infinite, technically an infinite series, but you have an infinite number of zeros at the end. And they're saying here that even makes sense with the binomial coefficient. So you can use that when k is equal to a positive integer, you can use this formula and it'll still give you the actual polynomial. And it reduces to the ordinary binomial theorem. All right, but coming back to, so they don't show how they prove it here, but I mean, you could do this on your own if you want. So yeah, if x is equal to 1, okay, if x is equal to +1, then you can only use k values between 0 and -1, including 0. Any other k value is not going to converge. If x is equal to 1. If k is greater than or equal to 0, okay, yeah, this is a little confusing here, so let me make sure I'm explaining this right. If k is greater than or equal to 0, anything greater than or equal to 0, then the series converges at 1 and -1. We're thinking about the endpoints. It converges at both endpoints if k is greater than or equal to 0. If k is less than or equal to 0 or greater than -1, then it converges at +1. It doesn't converge at -1. Now, if k is less than -1, then it doesn't converge at -1 or 1. So that's the endpoint behavior. All right, so now here's an example. It says find the Maclaurin series for this function. And so we can write this. We know that this is so 1 over 4 minus x to the 1/2 power, right? 4 minus x to the 1/2 power, but we learned in the previous section, we saw how we can keep manipulating this to get, it's going to be 1 plus minus x, and you're going to factor out a 4 to the 1/2, right? We worked a bunch of examples like this, and you can eventually get to this form. So you can use the binomial series with k is equal to -1/2 and replacing the x by minus x over 4. And so they take out the 1/2 factor. There's -1/2. There's minus x over 4. And what you're going to have to do is, with this binomial coefficient, the only way to work with these is you're going to have to expand it out with like the first 4 or 5 terms. So here they do 1, 2, 3. They do the first 4 terms and just try and find a pattern in these first 4 terms. They simplify it. They do the first 4 terms, simplify, and try and find a pattern. They find a pattern, and here's the formula. So they could just put this a sub n directly into the power series with the sum symbol, but instead they write it out like this. Okay, and yeah, there's something that I don't think I've mentioned much about this before. This is something good to note. So what's the radius of convergence here? Well, what you're going to do is, you know that the original 1 plus x to the k, assuming k is not a positive integer, that converges when it's from 1 to -1, right? And you could state it like this. That's what the limit ended up coming out to. Well, all you're going to do is you're going to take minus x over 4 and put it, and then solve that to get the radius of convergence. Now, as far as the endpoints, I'm curious if the endpoints still follow my guess would be that the endpoints follow the same rule, follow this same rule here, but they don't state that officially. I mean, it'd probably just be good to go ahead and check yourself. Okay, so that is the binomial series.